An uncrewed aerial vehicle, or UAV, navigates its environment using onboard computers and sensors, removing the need for a human pilot on the airframe. Every UAV design is governed by a strict engineering tension. Designers must continuously balance the energy required for vertical lift against the aerodynamic efficiency of forward flight. The laws of physics dictate that these operational forces oppose one another. No single platform can simultaneously maximize stationary hover stability, heavy payload capacity, and long-range endurance. To navigate these constraints, systems engineers use a multi-dimensional taxonomy matrix. This framework allows for the evaluation of different platforms based on their specific performance compromises. Precise UAV classification requires mapping an aircraft across 4 distinct vectors: its structural morphology, its universal avionics stack, its level of autonomy, and its physical scale. Understanding these strict physical trade-offs enables the design of mission-specific aerial systems. Avoiding the inefficiencies of an all-purpose machine requires a rigorous adherence to these engineering limits. This 3-axis radar chart maps the performance profiles of the primary structural platforms. The shaded area represents the multi-rotor morphology. Because these aircraft use downward-facing propellers to generate thrust, they possess excellent vertical takeoff and landing capabilities, spiking high on the hover axis. Within this category, quadcopters serve as the standard for general balance. When a mission requires lifting heavy industrial payloads, like cinema cameras or LiDAR sensors, engineers scaled the design to hexacopters and octocopters, which distribute the load across 6 or 8 motors to provide necessary mechanical redundancy. However, maintaining lift through continuous motor rotation incurs a high energy cost. Consequently, the multi-rotor profile drops low on the endurance axis, with typical flight times limited to 20 to 50 minutes due to high power consumption. Overlaid on the chart now is the fixed-wing morphology. These platforms resemble conventional airplanes, relying on the forward momentum of air passing over wings to generate lift, rather than continuous motor output. This aerodynamic approach results in significant energy efficiency. Fixed-wing platforms stretch far out along the endurance axis, achieving continuous flight durations of 1 to 12 hours, which is ideal for large area mapping and pipeline inspection. This efficiency is traded for stationary control. Fixed-wing platforms drop to 0 on hover capability. They cannot hold a position in midair and require substantial runway space or specialized launching infrastructure to operate. The choice between rotary and aerodynamic lift dictates the operational profile of the aircraft. A mission is optimized either for spatial precision in a confined area or for temporal persistence over a large distance. Specialized morphologies attempt to expand these performance boundaries. The single-rotor profile, seen here, offers significantly greater payload capacity and endurance than a multi-rotor, allowing it to carry the heaviest industrial sensors. This performance boost results in a trade-off of mechanical complexity. Single-rotor systems rely on large rotor blades and intricate mechanical linkages, necessitating high levels of frequent maintenance. The hybrid VTOL platform attempts to bridge the gap between hovering and forward flight. It combines multi-rotor vertical liftoff with fixed-wing forward flight efficiency, creating a wide, balanced area across both hover and endurance axes. Hybrid VTOLs achieve 2 to 10 hours of flight without requiring a runway. This configuration is used for emergency medical delivery and long-distance logistics where landing space is limited. Executing dual capabilities on a single airframe forces a shift toward extreme mechanical complexity. The versatility of a hybrid system is bought with higher maintenance requirements and sophisticated control systems. Regardless of the exterior morphology, the aircraft requires a stable method of control. Every modern UAV relies on a universal hardware stack to establish digital control over its physical movements. This wireframe diagram highlights the system's central processing unit, the flight controller. This component receives digital commands and translates them into physical aerodynamic adjustments. The flight controller requires continuous telemetry from orientation sensors, specifically the Inertial Measurement Unit, or IMU. This unit combines an accelerometer and a gyroscope to track the aircraft's pitch, roll, and yaw in real time. External spatial tracking relies on a barometer to measure atmospheric altitude, alongside a GNSS receiver that feeds geographic positioning coordinates to the central processor. During the actuation phase, the flight controller sends logic signals to the electronic speed controllers, or ESCs. These modules translate those signals into precise electrical currents, driving the exact RPMs needed at each motor to maintain the desired flight path. This universal closed-loop avionic stack standardizes uncrewed flight. It provides the mathematical stability necessary to control even aerodynamically unstable frames through software algorithms. Beyond morphology, platforms are classified by physical mass. This scale ranges from sub-250-gram nanodrones for indoor use to heavy multi-kilogram frames designed for long-endurance missions. This scatterplot maps physical size against autonomy. At the base of the y-axis is remote-controlled piloting, which requires a human operator to execute every micro-adjustment manually. Further up the y-axis are GPS-assisted systems. These enable the aircraft to execute automated spatial holds, follow pre-programmed waypoints, and trigger autonomous return-to-home functions without constant pilot input. At the top of the axis are fully autonomous and AI-powered systems. Onboard processors use mission planning software to identify targets and navigate obstacles independently, requiring zero real-time human interaction. These levels of autonomy define the operational range. While medium-range flights typically reach 50 kilometers, specialized autonomous platforms can operate beyond visual line of sight at distances exceeding 200 kilometers. The physical mass of a drone restricts the size of the sensor and processor payload it can carry. This capacity directly limits the onboard computational power, which determines the maximum level of autonomy and operational range the platform can achieve. Every drone functions as a specialized configuration of morphology, avionics, mass, and software, precisely tuned to meet specific operational goals. Consider the requirement to continuously inspect 150 kilometers of remote energy pipeline using heavy thermal imaging sensors. The decision tree for this mission identifies a hybrid VTOL for its range and takeoff capabilities. The mission requirements dictate a medium size to carry the thermal sensors, which provides the payload capacity for autonomous AI and enables beyond visual line of sight range. While onboard AI processors and sensory equipment will rapidly evolve, the thermodynamic trade-offs of lift generation remain permanent physical constraints on UAV design. Advancements in autonomy software are being used to offset these mechanical limitations, moving operational capabilities into increasingly long-range, automated domains. Applying this multidimensional taxonomy allows engineers to translate inherent aerodynamic compromises into successful, automated mission outcomes.
Please like, share, and subscribe to my channel for more great content.